Welcome back to Stack Lessons. In this lesson we're tackling document extraction and pre-processing for RAG pipelines, one of the trickier topics on the exam. Let's break it down. By the end of this video, you'll know exactly which Python package to reach for when a document lands in your pipeline, and why picking the wrong one quietly destroys your retrieval quality before the embeddings even run. We're covering the format to load a matrix every generative AI engineer ends up learning the hard way, plus the Databricks-native option that increasingly replaces the open-source stitching. In Episode 5, we saw DataDino wire up the information extraction brick to pull 6 fields out of their excavation PDFs: genus, species, era, dig site, depth, and condition. We mentioned that AI parse document handled the PDF pre-processing, and that AI extract did the structured pull. Today we go one layer down. Before any agent or brick can extract anything, somebody has to turn raw bytes into clean text, and the tool you pick depends entirely on what kind of file you're holding. 5 terms anchor this video. pypdf, also known as pyptfloater in LangChain, pulls selectable text out of digital PDFs page by page. Unstructured partitions complex documents into typed elements across many formats. pytesseract is the Python wrapper around Tesseract, the open-source OCR engine, the one that turns pixels into letters. BeautifulSoup is the HTML parser that lets you prune noise tags before extracting text. And I_parse_document is the Databricks-native SQL function that handles PDFs, images, DOC, and PPT files at scale, right inside the lakehouse. Every quarter, 40,000 pages land in DataDino's Unity catalog volume. And they don't all look alike. Some are clean excavation reports, modern PDFs, generated by software, with text you can highlight and copy. Some are scanned 1970s field notebooks, pings of faded handwriting, with no underlying text layer at all. And some are museum exhibit drafts, a strange mix of HTML web copy and docx files from the curators. If you point one loader at all of them, you will silently lose entire categories of content. Pages that look fine in the bronze table, but contain nothing the embedding model can actually use. Here is what makes extraction the most consequential stage of the entire RAG pipeline. Every layer downstream, embeddings, the vector index, the retriever, the prompt, the model, assumes that the text you fed in actually represents the document. If extraction returned an empty string, or a wall of cookie banners, or garbled OCR, the embeddings dutifully encode that garbage. Retrieval returns the garbage. The model answers from the garbage, and nothing in the stack tells you what went wrong, because technically, nothing crashed. Think of it like keys and locks. A digital PDF is a deadbolt. pypdf turns it instantly, with no fuss. A scanned PDF is a padlock with no keyhole at all. Only the OCR bolt cutter, pytesseract, gets you in. Using pypdf on a scanned document is like jamming a deadbolt key into a padlock and wondering why nothing happened. There is no master key for document extraction. You pick the tool that matches the lock. Here is the matrix you want in your head. A digitally born PDF, the kind generated by software, goes to pypdf, also known as pyptfloater. A PDF with complex layouts, tables, or docx and pptx siblings goes to Unstructured. A scanned page or image-only file goes to pytesseract, and only pytesseract. A web page goes to BeautifulSoup. Truly exotic formats, RTF, EPUB, Open Document, go to Apache Tika. And when you're processing documents at scale on Databricks, I_parse_document is the native option that replaces most of that open-source stitching. Match the source type to the tool. There is no universal default. Start with pypdf, because it is the simplest case. It is a pure Python library, and LangChain exposes it as pyptfloater. It walks a digital PDF page by page, pulls out the selectable text layer, and hands you back one document object per page, with the source path and page number stored as metadata. When your PDF was generated by software, a financial report, an academic paper, a modern excavation report, this is the fastest and simplest choice. Do not reach for anything fancier. The whole thing is 3 lines. Import pypdef loader, point it at the file, call load. What you get back is a list, 1 document per page. Each document carries the page content as a string and the metadata as a dictionary, including the source path and the page number. That page number is what makes citations possible later, when the chatbot needs to tell a visitor exactly which page of the excavation report it pulled the answer from. Unstructured is the next tool up. Instead of returning a wall of text, it partitions the document into typed elements. A title is labeled as a title, a paragraph is labeled as narrative text, a table is labeled as a table, and it handles a wide range of file formats through one API, including PDF, docx, PPTX, HTML, and email files. It is also the right answer when your corpus is mixed, when some files are PDFs, some are Word documents, and you want one library handling all of them. And it is the right answer when a PDF has tables, headings, and complex layout that you want preserved. Here is the failure mode that catches almost every engineer at least once. Think of Unstructured as a brilliant editor. Hand it a well-typed manuscript, and it will break it into chapters, headings, and footnotes beautifully. But hand it a photograph of a 1970s field notebook, and it just stares. It does not do OCR out of the box. You will get empty documents back. No exception, no warning. Your pipeline will look healthy. Your retrieval will quietly fail. The fix is to recognize that scanned input needs a different tool entirely. The pypdf maintainers say it themselves, right in the official documentation. pypdf is no OCR software. It will not be able to detect those failures. It will never be able to extract text from images. Read that second sentence again. It will not be able to detect those failures. That is what makes this so dangerous. You don't get an error, you don't get a warning, you get an empty string, and your pipeline moves on. Look at what that actually looks like in practice. We ran pypdf against a scanned 1973 field notebook. 14 pages loaded. Every single page reports a text length of 0. And then, at the bottom, extraction completed successfully. No exceptions, no warnings, no hint that something went wrong. If you don't have a check that flags empty pages downstream, this entire notebook quietly disappears from your knowledge base. The reason this happens is fundamental. A digital PDF stores actual letters. The character T, the character H, the character E, they're encoded as character codes, and pypdef reads those codes directly. A scanned PDF stores pixels. It is a photograph of a page. There are no letters in there at all, just colored dots arranged in shapes that look like letters to a human eye. pypdef reads character codes, so on pixels, it has literally nothing to read. OCR is the translator that looks at those pixel shapes and reconstructs the letters they represent. Here is the fix. PDF2 image renders each page of the PDF as an actual image at 300 dots per inch. Then pytesseract, the Python wrapper around the open-source Tesseract OCR engine, processes each image and returns the recognized text. Notice the lang parameter. Tesseract defaults to English, and if you forget to pass the right language for a Japanese or Korean document, it will silently produce nonsense. The shape of this code is the canonical answer for scanned input in production pipelines. OCR is not free. Look at the relative cost. Reading the text layer of a digital PDF with pypdf is the baseline, call it 1 unit of work. Unstructured on its fast strategy is roughly 3 times that, because it's also classifying element types. OCR with Tesseract is roughly 1,000 times slower than reading a text layer. That means you do not run OCR on every page indiscriminately. In a real pipeline, you check whether the page has a text layer first, and only fall back to OCR when it doesn't. Quick halfway check: digital PDF goes to pypdf, the simplest and fastest path. Complex layouts or mixed document formats go to unstructured, but remember, it does not do OCR. Scanned or image-only input goes to pytesseract, and that is the only correct answer. With those three in your head, we can move on to HTML scraping, the broader exotic format case, and the Databricks-native option that ties it all together at scale. For HTML, BeautifulSoup is the standard tool. The thing to watch for is that calling get_text on the raw soup pulls in inline JavaScript, embedded CSS, navigation menus, and footers, all mixed in with the article. The fix is to call decompose on the noise tags first: script, style, nav, footer, and header. That permanently removes them from the tree. Then when you call get_text, what's left is the article content. 2 lines of pruning save you from polluting every chunk you produce downstream. Look at the difference. On the left, get_text alone. Inline JavaScript leaks into the output. CSS rules show up between paragraphs. The same navigation menu appears on every page. Cookie banners and footers appear in every chunk. On a typical news web page, 30 to 50% of the tokens are pure boilerplate. On the right, after calling decompose first, the noise tags are gone. Only the article content survives. Your embedding space stays clean. You use up to 60% fewer tokens, and retrieval ranks on actual signal rather than on the Chrome around the page. Apache Tika is the answer when your corpus is genuinely exotic. Formats like RTF, EPUB, and Open Document that Unstructured doesn't reach. Under the hood, it is a Java-based toolkit, typically run as a server with Python bindings on top. It detects the MIME type of a file and extracts text plus metadata from over 1,000 formats. The trade-off is that Tika optimizes for format breadth, not for RAG-friendly structure. If your corpus is dominated by weird legacy formats, reach for Tika. If it's mostly modern documents, you'll be happier with Unstructured. Now to the Databricks-native option. A Databricks engineering blog post describes it like this. The I_parse_document function allows you to process millions of complex documents, tables, figures, diagrams, with the power of groundbreaking artificial intelligence research in one single SQL function. The key phrase there is millions of documents in one SQL function. Instead of stitching pypdf, OCR, and custom layout code together in a notebook, you write a select statement, and the platform parallelizes the rest. Here is the pattern you should recognize. The read files function pulls the raw bytes out of a Unity catalog volume as a binary file column. I_parse_document takes that binary content and returns a variant, a semi-structured type containing a list of elements. Each element has content, a type label, a bounding box, a confidence score, and a page number. That bounding box is what lets DataDino cite the exact pixel region of the PDF when the chatbot answers a question. Know the limits before you build this into a pipeline. I_parse_document handles PDFs, images, DOC and docx, and PPT and PPTX. Each file can be up to 500 pages and up to 100 megabytes, and you need Databricks Runtime 17.3 or later. If you have an archival legal PDF that's 800 pages, you split it first. If a file is 150 megabytes, you split it first. Those numbers come straight from the official documentation and they're worth memorizing. The real power comes from chaining the two functions. I_parse_document converts the raw bytes into that variant of typed elements. Then I_extract pulls the named fields you actually care about. For DataDino, that's genus, species, era, dig-site, depth, and condition. Both functions run inside the lakehouse, inside the security perimeter, in parallel across your cluster. And as we covered in episode 5, I_extract is the function that powers the information extraction brick under the hood. The brick is the high-level template. These two SQL functions are what it's actually calling. Once the text is out, the next job is content filtering. Think of boilerplate as the fat on a steak, the repeated headers, footers, navigation menus, and cookie banners. If you grind the fat into the burger, every bite tastes greasy. If you embed the boilerplate into your vector store, every retrieved chunk sounds like another subscribe to our newsletter prompt. Filtering extraneous content is an explicit data preparation skill on the certification, not a Polish step you can skip. The cleaner the input text, the cleaner the embedding space. The other pre-processing step worth knowing is deduplication. Near duplicate chunks are poison to retrieval. They inflate scores for the wrong reasons and they bias the model's context. The standard approach is min-hash plus locality-sensitive hashing. Min-hash turns each document into a shingled signature. Locality-sensitive hashing buckets similar signatures together so you can find near duplicates fast. Spark ML libships a min-hash LSH transformer that runs this at lakehouse scale. For context, Eleuthia AI's Pile project used this exact technique to drop roughly 30% of the common crawl corpus before any other filtering. Duplicates are a much bigger fraction of real-world data than most engineers expect. Here is how DataDino's actual pipeline ties this together. Raw files land in a Unity catalog volume. A MIME-type router inspects each file and dispatches it to the right loader. Application PDF with a text layer goes to pypdf. Image ping or a scanned PDF goes to pytesseract. HTML and docx go to Unstructured. All three loaders write into the same delta bronze table, called docs_raw. The bronze schema is unified: source_path, file_hash, ingest timestamp, the raw bytes, and the extracted text. The branching happens upstream of the table, so anything downstream sees one clean shape. Why store the raw bytes in bronze when you've already extracted the text? Because bronze is your photo negative drawer. You don't throw out the negative just because you printed the photo. 6 months from now, I_pars_document will be better. Tesseract 6 will be out. You'll want to re-extract everything with a smarter loader. If you kept the raw bytes, that's an SQL query. If you only kept the extracted text, you're refetching 40,000 pages from 40,000 source locations. Always keep the negative. Here's how the official guide phrases it. Choosing the appropriate Python package to extract document content from the provided source data and format. That is the entire framing of today's lesson. Source data plus format dictates the package. The matrix we walked through is the answer key. Here are the rules to commit to memory. If the source is a digital, text-selectable PDF, use pypdf or pypdfloader. If the source is a mixed layout PDF, docx, or pptx, use unstructured. If the source is a scanned PDF or an image-only file, use pytesseract, pair it with PDF2 image to render the pages. If the source is a web page or HTML, use BeautifulSoup, and remember to decompose the noise tags before extracting. And if you are running batch document processing on Databricks at scale, reach for I_pars_document, and chain I_extract on top when you need typed fields. 5 things to lock in. First, extraction fails silently. pypdf returns empty strings on scans, unstructured returns empty documents, and no exception is raised. Always verify your text length before you embed. Second, scanned and image-only inputs need OCR, and pytesseract is the only correct answer. Third, BeautifulSoup is for HTML, and you must decompose script, style, nav, and footer before extracting text. Fourth, on Databricks at scale, I_pars_document plus I_extract replaces the open source stitching within a 500-page and 100-megabyte ceiling. And fifth, always land the raw bytes in a delta bronze layer so you can re-extract later. Now let's see how well that landed with a quick 5-question quiz. Question 1. A data engineer at a research lab needs to extract text from a corpus of scanned 1960s lab notebooks stored as image-only PDFs. They try unstructured payloader with the default fast strategy, and the pipeline runs without errors, but downstream retrieval quality is terrible. What is the root cause and the correct fix? Is it A, the pipeline needs more compute, increase the cluster size and rerun unstructured? B, replace unstructured with pypdf, which handles scanned PDFs natively? C, use BeautifulSoup with HTML.parser to extract the embedded text layer from the PDFs? Or D, unstructured does not perform OCR by default, switch to pytesseract paired with PDF2 image to convert pixels to text? Take a moment to think about it. The answer is D. Unstructured on its fast strategy doesn't OCR scanned images, it silently returns empty documents and the pipeline reports success. Scanned input requires an OCR engine, and pytesseract paired with PDF2 image is the canonical fix. pypdf is wrong for the same reason as unstructured, it can't read pixels, and BeautifulSoup is for HTML, not PDFs. Question 2. A team is building a RAG pipeline over scraped news articles. They use BeautifulSoup and call get_text directly on the parsed HTML, then chunk and embed. Retrieved chunks are dominated by repeated navigation menus, cookie banners, and inline JavaScript. What is the simplest correct fix? Is it A, switch to Apache Tika, which handles HTML boilerplate automatically? B, increase the embedding model's context window so boilerplate gets diluted? C, call decompose on script, style, nav, footer, and header tags before calling get_text? Or D, replace BeautifulSoup with unstructured.partition.html, which removes navigation by default? Take a moment to think about it. The answer is C. Get_text on its own preserves the content of script, style, nav, and footer tags. Walking those tags and calling decompose first permanently removes them from the DOM. So only the article content survives. Tika doesn't magically strip HTML Chrome, and a bigger context window only hides the pollution, it doesn't fix it. Question 3. DataDino wants to process a quarterly batch of 40,000 excavation PDFs entirely within Databricks SQL, parsing each document, and then pulling out 6 structured fields per record: genus, species, era, dig site, depth, and condition. Which approach matches the platform-native pattern? Is it A, use I_parse_document over a binary file read to produce variant elements, then chain I_extract to pull the 6 fields? B, use unstructured pfloader in a Python notebook for parsing, then call I_extract in SQL on the resulting strings? C, use Apache Tika via a Python UDF to parse each PDF, then write a regex extractor for each field? Or D, use pypdf in a pandas UDF, then prompt a foundation model to return JSON with the 6 fields? Take a moment to think about it. The answer is A. The Databricks-native pattern is I_parse_document for the parse step, producing a variant of typed elements with content, type, bounding box, and page metadata. Then I_extract chains on top to pull the named fields. Both run as SQL functions inside the lakehouse with automatic parallelization, no Python UDFs, no regex, no extra stitching. Question 4. Let's test a concept from an earlier episode. DataDino's senior architect chose RAG over fine-tuning for the museum chatbot because the paleontology team actively revises extinction date records as new fossil evidence emerges. Which property of RAG made it the correct architecture choice for this situation? Is it A, RAG produces lower latency responses than fine-tuned models at inference time? B, RAG retrieves current information from an external source at inference time, so updated records appear in answers without retraining. C. RAG models are always cheaper to operate than fine-tuned models of equivalent size. Or D. RAG eliminates the need for prompt engineering by automatically generating optimal prompts. Take a moment to think about it. The answer is B. From episode 4, the architect chose RAG specifically because the paleontology team's edits need to reach visitors without retraining cycles. RAG retrieves from an external data source at inference time, so an updated extinction date in the delta-backed vector search index shows up in the next response. Latency and cost weren't the deciding factors, currency of information was. Question 5. An engineer is designing a delta bronze layer for a mixed format document pipeline. A colleague suggests skipping the raw bytes column to save storage, since the extracted text is already in the table. What is the strongest argument against dropping the raw bytes? Is it A. Unity Catalog requires a binary column to enable column-level security on document tables? B. Storing raw bytes is the only way to compute a file_hash for deduplication. C. Keeping raw bytes allows re-extracting with improved loaders later without refetching every source file. Or D. Delta Lake does not support tables that contain only string columns. Take a moment to think about it. The answer is C. The whole point of bronze is durability against future loader upgrades. When I_parse_document gets better, when Tesseract 6 ships, when a new layout-aware parser shows up, you re-extract from the bytes you already have, instead of refetching 40,000 source files. Bronze is your photo-negative draw. The other options are either flat-out false or beside the point. That's it for document extraction and pre-processing for RAG pipelines. Drop a like if this clarified things, subscribe so you don't miss the rest of the Databricks GenAI Engineer Cert, and I'll catch you in the next video.